Yeah, so thank you to Jose for inviting me to speak to you all today about a topic which is very dear to my heart, memory profiling. So, before we start, I think I could talk about any one of these slides for a whole hour. So, if you have any questions at any point about any of the slides, raise your right hand. On the other hand, I've been told that I do a lot of arm waving in presentations when I gave my last presentation. So if there's too much arm waving going on and too much enthusiasm, raise the left hand. Okay. So we've got... Right, okay, yes.
Stage left, or...?
If it's just sensory overload, both hands at the same time. Okay, and we'll take a small breather. So memory profiling is a topic which I get really enthusiastic about, and I'm very pleased to be able to speak about it to this audience, because giving a kind of retrospective talk over the last 5 years of work feels very, very cozy somehow. It's very nice to look back at everything you've achieved that you didn't really expect to get to when you started 5 years ago, or however long ago I started, and actually think, wow, we have come a long way in our ability to memory profile Haskell programs. But of course, it was not just me on my own who did this. There was also a long list of people which I compiled in the previous talk who have been helping along the way, and quite a few of them here today. So I think Finley is over there at the back somewhere. Ben is here today, or he's not here? Ben's coming later. Hannah's here tomorrow. Andreas is over there as well. So there's quite a few people in this room who have helped on this memory profiling journey, and that's been hugely, hugely helpful. So when you're doing a retrospective, it's quite useful to start at the beginning and where we started from. And I went back to the GHC 8.10 user manual, which was approximately 5 years ago. And I got this picture out of the memory profiling section, and I attempted to understand what it was trying to show me. And despite now being an expert in memory profiling, I still didn't have the foggiest about how I'd use this information in order to debug an actual problem. There are no colours. This is an actual screenshot. The memory use of this program is, 30 kilobytes? That's great. Why are we debugging this problem in the first place? And although I have some uncanny ability occasionally to detect a problem from minimal information, I cannot detect what is next after this ellipsis here and what the rest of this information tells me. It is just not in the profile. I have no means of knowing anything about it. So overall, on Friday, October 2nd, at 1 minute past 3 in 2015, we didn't have the foggiest. But of course, we wanted to improve the situation, because memory profiling is very important for Haskell programs, because Haskell programs can use lots of memory. I've already heard much talk of programs using an extraordinarily large amount of memory, and people often have not had the opportunity to investigate why that is. You just get a bigger server, or you just accept it, which is not really a great state of affairs. It's okay to accept something if we understand, at least, why we're in the situation to begin with. Allocation in Haskell programs is not typically very obvious. High-level language, which is compiled to a core language. If you use a higher-level construct, you're not thinking, how is that affecting my memory usage? After that, you have an optimizer, which significantly changes memory behavior. In my experience, you have different optimization passes, like strictness analysis, and even inlining can just change significantly how the memory of your program behaves. I'm sorry, everyone, but the programmer mindset is not focused on allocation. That is a hard truth. People do not generally care that much about the memory usage of their programs. They're not thinking about it, and that's fine. But we at least have to have the ability to debug it if it starts going seriously wrong. And finally, the one people might immediately think of is that lazy evaluation does take significant experience to reason about, whatever people tell you. Like, when you're writing a program, it takes years and years of experience to start thinking, what am I actually creating when I write an expression? Am I creating a thunk? Is it going to be evaluated? What am I retaining? these are things that I've only developed through developing all these tools, and most people are never ever seriously thinking about. And that is also fine. It's complicated because now we have the tools in order to analyze, after we've written the program, what has actually happened and fix things in a straightforward manner. Right, so we started out from this grayscale profile, and there are two axes. Oh, I put my hands up already. I lasted for like 5 minutes or so, but it was too much. Right, we have gone two different axes. We on one hand have gone on the, which one did I do first? The instrumentation axis. So the compiler now has many more ways of telling us information about what is happening. There are different modes that can be used to get lots more information, which then the interaction axis takes over and displays them. So we've kind of independently, co-dependently working on these two different axes, and they synergize together to allow you to investigate these kinds of issues. So on the instrumentation axis, we have these new profiling modes, new ways to access the event log, new runtime system APIs. These are primarily changes within GHC itself. On the interaction axis, there are two cornerstone tools in memory analysis, which people are quite familiar with. The first one is event logs for HTML, which allows you to give a high-level visualization of memory usage of a program. And then secondly, there is GHC debug, the powerful machine to get those true, deep, precise insights into the runtime. So we use these tools now, we use these new APIs, and we use these tools in order to get a clear handle on what is going on with the memory of the program. So in this talk, I'm going to essentially describe, most of the talk is going to be about event log to HTML, and some of the talk is going to be about GHC debug. And I want to kind of get really give kind of like an impression of how I use these tools, and an impression of like when I look at this profile, what am I actually looking at? Because I think there are a lot of insights that you can gain which are somehow non-obvious and are not written down anywhere, and I explain to a lot of people independently that really allow you to squeeze the most out of these analysis tools. So I suppose really there are like three axes that are, there's the instrumentation axis, there's the interaction axis, but then also thirdly the interpretation axis, which is potentially the most difficult one to maybe there's also four, the intuition axes as well. Maybe I'll think of another later, but this is what memory does to me, it inspires me. Okay. Right, so these are kind of the tools that we're going to use, but firstly we're going to take a step back and think about like what are the kind of questions that we're going to want to answer about memory in the first place. The primary question that people want to know about memory usage is what closures are live, like what is actually using the memory that my program is reporting. That is the most fundamental question of memory usage in Haskell programs, and one that can get you a long way to understanding what is going on. Once you've understood that, the next question is typically, well, it's alive, but why? Like, closures are kept alive by other closures, which are kept alive by other closures, so on and so on. And unless you can, in a precise manner, determine why something is kept alive, you have very little hope of reducing it. Since if you can't stop it being used by everything, then it must always remain alive. And finally, like a slightly different question is, well, obviously your program needs to use the heap for something. You want some data alive in your program, but then there is your program is usually separated into phases, or your data has a lifetime. You want it to be allocated, used, and then deallocated. And so knowing when a particular closure is allocated, during what phase, can be extremely useful when trying to debug these lifetime issues. So I was classically trained, and I was taught to program using invariants. And I was told that you must never write a program without first specifying, you must never write a loop without first specifying what the loop invariant is. And this has clearly deeply affected me throughout the rest of my life. Because before we start debugging memory issues, or before we start writing any program, we must first consider what are our memory invariants of our program. And I really wanted to get this slide in because it's all well and good. You start writing your program and you use a lot of memory. And then you look at a profile and you look at it and you're like, oh, this is so pretty, it's now in colour. But without the question to ask of the profile, you really are just guessing at what the problem is. I always ask people, I always ask my colleagues when they ask me about a memory issue, what are we attempting to debug? What is the memory invariant of the program which we're trying to establish? Because even establishing very simple things then gives you a beeline into interpreting the profile, the third axis. So an invariant typically split into two parts. Firstly, the timeline, before, after, during, between. Like what am I expecting in a certain period of my program? And then secondly, the heap predicate. What am I expecting the memory to be like during that period in the program, or before that period in the program, and so on. For example, a very common one, no constructors are alive of a certain type after a certain point. When my program has finished processing the text file, no strings from the original text file are alive. A very simple invariant. Is it true about your programs? We've got a yes. That's it, I'm done. So people might try and achieve this using strictness or so on and so on. But by using strictness, you're attempting to establish an invariant. So why don't you write it down, and then when it goes wrong, it's very easy to verify if it's true or not using these tools in this presentation. A more complicated one, there are exactly 5 live closures of type T. This requires a bit more precise thinking, but for example, when you're writing a compiler, you want one closure for each module you are compiling for certain data types. It's simple. And I can check it extremely easily. And if it's false, then I can fix it really easily because I'm looking for something precise. There's up around 20,000 byte strings. Well, this is imprecise in some sense, but if the number is 200,000 rather than 20,000, or 2 million, or 2 billion, then something has clearly gone wrong. So even setting quite imprecise invariants is a long way to getting you to think about what am I trying to achieve in my program, what is alive when, so on and so on. And finally, a more complicated kind of invariant, like no closures of type T are reachable from closures of type Q. This might be like from a thunk, I don't want to reference a particular type of object, or from a data constructor, I don't want any thunks to be reachable from that. I want it to be deeply forced. So this is kind of more of a kind of like complicated structural invariant rather than like a counting invariant. But these can also be extremely useful. So I'd encourage people to think very carefully about their memory invariants even before trying to debug the memory usage of their program. Because you might find out that when you think about it, you've done something extremely stupid to begin with, and you don't even need to do any of this. So that would save everyone a lot of time. So what's some memory invariants that I have checked in the past? Well, after modules finish compiling, no source syntax is retained. It's quite a simple one which GHC did not uphold for a very long time, obviously. At the end of the program, retained data is fully forced. It's pretty straightforward. There's libraries like nothunks, Theo is going to give a talk about it, so on and so on. Obviously, GHC did not uphold this for a very long time, but guess what? No, we could investigate it and we could fix it once we wrote down the invariant and we had the tools. Right, so memory profiling is the investigation into the violation of invariants. That's my profiling philosophy. Okay, so you've been down the pub, you've thought about your invariants very hard over a beer or two, and now something's not quite right. What do we do? So these days, the main way of inspecting what is going on with runtime of a Haskell program is what's called the event log. The event log is a binary log of runtime events. You get the event log by using the runtime option plus RTS-L. In all recent versions of GHC, you can do this on any Haskell binary. It's always enabled by default, and it will give you a log of what the runtime is doing during the execution of your program. What is the runtime doing? A lot of stuff. There are user events, which I'll get into later, the thread events, profiling events, GC events, memory events, STM events, so on and so on. This file can get quite large, but it does give you the ability to inspect these kinds of things to do with the runtime. So if you want to get information about the runtime, you use the event log. When you use plus rts-l, it produces a program name.eventlog file. Once you have the program name.eventlog file, this can be ingested using the analysis tools. So if you care about memory, maybe eventlog to HTML. If you care about parallelism or other things, then thread-scope might work, or you might have to write your own analysis script if no one's got there first. Theo, are you here?
Yeah.
Does it look like this still, or is this an old?
Yeah, it looks similar, but it will be GTK 3, so it'll look slightly nicer.
Looks slightly nicer. Okay. Okay, it looks quite 2000 still.
No, is this?
This is an old screenshot from my computer. Yeah. Okay. Yeah, okay, so thread-scope is quite an old tool at this point, but there's still nothing better for debugging things to do with parallelism and concurrency. So the main means are using these offline analysis tools. You run your program, you get an event log, you pass it into these tools. There is also another way of consuming the event log, using these event log live libraries. And what these do is when you start your program, it creates a socket, and then if you want to look at the event log, you connect to this socket, and the event log is sent over the socket to whatever you've connected to. So you can connect to an analysis tool, you can connect over a server, or whatever you want. So we wrote question.
Is that Grafana?
So this is Grafana. So we have written this. We wrote this. Well, I think Finley wrote this. Suite of tools that take an event log and put the information from the event log into Grafana, and InfluxDB, which is going to be displayed using Grafana. As far as we know, though, no one uses this.
Is this all open source?
Yeah.
Great.
Yeah, so I mean, I wouldn't put this like as far as we know, we think this is quite useful, but no one uses it. So we might be completely wrong. But this example here is we have got a running process, a server, and then we've connected to the server whilst it's running. We get the event log from the server, and there's a button in Grafana you can click, and when you click it, it does a heat profile, and it populates the Grafana dashboard with the information about the heat profile, which sounds quite ergonomic to me, but yeah, no one is using it, so. Yeah.
Have you announced it publicly before right now?
Did we? I don't know.
We had a blog post.
Yeah. Well, okay. This is the public announcement of these tools that. Yeah, it's pretty good. So yeah, so that's the other way, but nothing really works with this yet because, like I said, we haven't publicly announced it until now. It seems like a strategic error, but one of only many errors I've made in my life. So, well, potentially that was the most interesting slide. I'll just stop. Okay, so once you've got your event log, you run event log to HTML on your event log, and so event log to HTML is about heat profiling, right? So if you care about like analyzing memory usage, which is what this talk is about, then you probably want to use your event log with event log to HTML. You run it on the event log, and it turns the event log into HTML, as the name suggests, and you get this nice little interactive chart. And even if you don't have anything to do with profiling yet, this can still be quite useful. Because the first graph of event log to HTML is this graph which is labeled heap. And heap tells you how the overall memory usage of your program, which it might be is what displayed in your system monitor or so on, relates to the amount of live data that your program has. And these numbers are going to be significantly different to each other because the runtime uses it allocates quite a lot of memory itself for doing runtime things, which are not just storing your data on the heap. So understanding that you may have you're trying to investigate a memory, your memory variable might be, my program uses less than 4 gigabytes of memory. Well, that is still not precise. 4 gigabytes of memory overall, or 4 gigabytes of live data. You first need to look at the heap graph to understand, well, what actually is happening here. Am I just in a situation where the runtime is using a lot, or am I in a situation where I have a lot of live data? And obviously the two are related somehow, but you at least need to think about it before you start deciding, am I going to modify garbage collector settings to reduce the memory, or am I going to change parts of my program to reduce the memory? So what do these bands tell you? So these are the key 3 measures of memory usage in the runtime. The red band at the top is megablock usage. So that is the biggest unit that the runtime will get memory from the operating system. That line corresponds to how much memory the process uses typically. So in this example, on the system monitor, it probably says that it uses 220 megabytes of memory. On the other hand, the green line, that's how much user data is live on the heap. So there's actually only 60 megabytes of live user data, but the runtime needs all this overhead between the green line and the red line in order to do its runtime things with these particular settings that I chose. And then the blue line, that's the block usage. So within megablocks, there are blocks, and each megablock may not be filled up all the way. So there are blocks allocated within a megablock. And this blue line tells you it's basically the sum of the live bytes plus the size of the nursery. So then using these information, you can say, well, the size of the nursery is the gap between the green line and the blue line. The gap between the red line and the blue line is things that the runtime is, various things the runtime might be doing. The green line is things I have done in my program. So that's where memory usage investigations typically start. Okay. So you get this for you can get this for any program without any runtime profiling options or anything. Yeah.
You mentioned intuition earlier. How do you build the intuition to know when the size between the red and the green is too big?
How do you build the intuition that the gap between these lines is too big, like red and green is too big? I suppose that's a good question. Like, you would typically expect this red line to be 4 times the height of the green line. That's not intuition, I guess. You come to events like this and people tell you things. It kind of requires knowing what the runtime is doing to know, which is not that obvious to a lot of people, I imagine. Red line is typically 4 times green line, is how it is, and if that's too much, then you can change some garbage collector settings to make it less. Anyone have a better answer than that? No, right. Yeah, Andreas.
One thing to look out for is if the ratio changes, then it might have a problem, right? If you look at the server profile, and as the time goes on, it goes from the red line is 3 times as much as the green line, eventually it's 20 times as much. You probably need something. That's
Yeah, like they changed over time.
even more important than the actual ratio.
Like what is typically happening in this particular profile here is, as the program starts, the red line and green line are much closer together, and then as the program allocates more, then the runtime, it retains more memory in anticipation that it's going to allocate again. So it retains like 4 times the amount of live bytes by default. And in this particular workload, it's just the program is constantly allocating. So the red line just goes up at the same time as well, at approximately 4 times the rate of green. But in some workloads, it might stop allocating here. And then there are various mechanisms that this red line will decrease back down towards the green line. But it is yeah, maybe like a blog post or something just about this graph would be interesting. You can also like see fragmentation sometimes in this graph, which is never really a problem unless you're doing something, you're allocating a lot of pin byte strings. But it's a good question. At least it's something to potentially investigate. Okay. Right. So once you've like looked at this this heap graph, which tells you like very, very, very high level stats about memory usage, then you probably want to start investigating the heap itself. And just as a very, very simple, brief refresher about how the heap in Haskell is structured, the heap looks like this. It's a rounded rectangle, which has square rectangles inside, which have other square rectangles inside. And essentially, everything on the heap has the same structure. At the top is an info table. The info table tells you about what is following in the body. And the body then has data and pointers, and the pointers point to other things on the heap. That's kind of it. So all these memory usage tasks, memory profiling tasks that we're going to investigate are going to be about essentially traversing these pointers and creating counts of various different things to do with these closures. That is heap profile. What heap profiling is all about in one slide. And it turns out there's quite a lot of different things that you can count. So it's really interesting. Right, so the info table tells you about the closure type and layout and so on and so on. Right, so far we haven't, by default the event log is not going to get any heap profiling information into it. And
sorry,
yes?
Terminology, so any heap object to use a closure.
Right, so yeah, in the run, everything's called a closure,
right.
But it's not everything is a closure as you might typically call it in other languages. It's just everything is called a closure in the runtime. And everything that's heap allocated is called a closure, just because it always has been.
And that's also the terminology that's used in the code base.
Yeah, Simon? Everything is called closure, right? And you're probably responsible for it. Yeah, yeah, that's just. It wasn't. For the record, it wasn't Simon Marlowe's idea. Okay. Okay. So then, when we're creating heap profiles, the task is to get more information into the event log about what is on the heap. So we need to instruct to the compiler at various points during the program, traverse the heap and record counts about what you find into the event log. How do you do that? Well, you pass an extra option to GHC. And the most useful one, or the one I always start with, is the HT option. And this does a profile by closure type. And what that means is that every time a particular interval, when the heap profiler runs, it traverses the whole heap, and it just counts for each different type of closure, so a function, a thunk, a constructor, a stack closure, primitive closures, so on and so on. It just counts how many of those there are. And for me, this is one of the most useful profiling modes because it gives you a more fine-grained view of what's going on. You don't need the profiling runtime, and you just gets you started with trying to understand what is going on with the memory usage in your program. So when I have run, so this is the same profile as before, and now we'll switch into interactive mode. How do I go full screen? F11. It worked. Right, thank you. So this is the output of event log to HTML. So as you can see, this is the slightly different heap profile to the one which was in the previous slide, but that exists still. So now I get this interactive profile, which is now segmented into bands based on the different closure types. And different closure types are some of the top most common closure types are given here. And it still is maybe like it's like what are we looking for? Like we're not really looking for anything particular in this example because we're not. But at least some things you can do. You can click on each of these different allocation points to see like how each different closure type changed over time. So I'm clicking on thunk 20 now. So these are thunks that have 2 pointers and no data. And you can see that, well, there's basically the same amount of things allocated throughout the whole program, but they do go up and down quite a lot. And I can't tell you anything about whether that's good or bad, because we have no memory invariance. But at least this is, you can think about your own programs and what you might want to discover here. Right, so this is the most basic view. So what is quite useful is that constructor closures are distinguished. So I've just clicked on that one, which, we have this problem with the ellipses again. It comes back to bite us after 10 years. We still haven't made as much progress as I thought. Anyway, so I can actually discover what this one is there, and these are list constructors. So I've clicked on this one, and now I can see like how the list constructors change over time. So at the start, there's like a big spike, and then it flattens out. And so I've not had to recompile my program to get this. I just pass an extra option at runtime, and I can get a heap profile out of what it's doing. So this can be sufficient for finding out what you want to find out. Right, so what is kind of not that great about this view is, well, it tells me that the top 10 or so sources of allocation, so takes up about half of the memory usage. But then there is also all this other category, which is still a significant amount of memory usage, and that might actually be where your problem is if you have like a lot more precise invariance. And that is where the detailed pane comes in. And it's really obvious when you think about it, but we just took the data from the event log and we put it into a table. And you can now search, like, yeah, so it's amazing. And now, rather than just getting the first 10 items, you get everything. You get single allocations of random things that only appeared in one heap sample. So you get a much finer grain understanding of what is actually going on in your profile. The other kind of useful technique or profile view is the line chart profile. And the line chart profile allows you more easily to see which bands are correlated with each other, which can be very useful, because we see lists at the top of the profile, but lists are used by lots of different places. So it can be quite hard to distinguish like what all the uses are. But if we can see that the list curve corresponds with another curve, then that can give you some kind of intuition about what the problem might be. So in this example, you can see how there are quite a few of the bands are quite random, like going up and down quite a lot, but then there are a certain few bands that from the start of compilation to the end of compilation increase linearly almost. So those are kind of like the data of the program in some sense, and the other parts are things that have existed for a long time for various reasons. So you can kind of use the line chart to correlate together different bands. Right, so back to the detail pane. So sorry, I didn't mention this, but the workload is GHC compiling all the Cabal libraries in GHCI. So Cabal syntax, Cabal install, like so on, all those libraries in one multi-REPL session. There's like 500 modules of GHC compiling them without the optimizer. Right. Okay, so back to the detailed pane. Detailed pane is honestly one of the most useful things. And so we start out from the left-hand side here. And the left-hand side gives you a very simple chart about what the profile of that particular band is. And on its own, maybe this is not that useful, but again, you really easily use this to correlate different parts of the profile together. In this example, you can kind of see that, well, iHash constructors and source spans follow a very similar pattern. It's not exactly the same, but it looks similar enough to the naked eye. And so therefore, I might reason that these ints were allocated to store numbers inside source spans. That kind of reasoning can occur in a detailed pane. So you can, and depending on what your program's doing, you get different shapes here, these two are kind of similar to each other. So you can kind of build that intuition up just by looking at this simple profile on the left. You get the name of the closure in full without any dots. If it's 1,000 characters long, it's printed. Don't worry, everyone. It will overflow the side of your screen, but you'll still be able to read the information. And then finally, on the right-hand side here, you have different statistics, which, to be honest, are of dubious benefit. But they tell you, firstly, like the total size underneath the curve of the graph, so the integrated size, like the footprint overall over the course of your program. And that is how all these bands are ordered. So that's why they're decreasing here. And then you get things like, okay, this is a linear regression done on the data. So where is the intercept? What is the intercept and slope? So if the intercept is higher, like if it's 1, then it's a flat line, and if it's 0, then it's a increasing line. And the slope tells you how steep it is. Like so. If the slope is closer to 1, then it's more like increasing linearly throughout the program. But then this one here is minus 0.2, so it's decreasing throughout the program. So those, I have attempted to use those, but to be honest, they're not that useful. What is really useful is being able to search things. So I've searched for home mod info there, which is one of these key data types within GHC. And then I can look at the particular allocations of that, and I often do this arithmetic in my head, so I would hover over here and say, well, that is 16,765. You might need glasses soon to read that, but then I take that number and divide it by the size of the closure, and that gives me the how many are live at that point. Which it would be nice if that number was reported in the profile, but that's just arithmetic I do regularly.
So just to be clear, when you're searching for, in this case, home mod info, that's just a data type in this particular code base.
Yeah.
If I were debugging my program, I could search for a data type in my code base.
But it depends what profile you're doing. So it just does a text search this field. So I can search thunk as well. And just because this profile has closure types, and for constructors it has particular constructors. So yeah. Right. So any questions about closure? Yes.
Where can we find the information on what the thunk 1101 is?
Where can we find information about what thunk 10, thunk 20, thunk 11, thunk 01, so on? What different closure types are? What does it mean? Well, the file closures.h in GHC source code. This is a good one. Anyone know where that information is? The GHC wiki, perhaps?
I have a ticket to add documentation to this.
Theo says he has a ticket to add documentation. Duncan?
But maybe the question really means, like, what is the thunk? I mean, okay, it's a thunk with 2 arguments, but, like, for what function?
Yeah, we'll get to that. But so is the question about which thunk, or is it about what are they? Yeah. Okay. Well, what is discoverable? Yeah. Michael.
Could we have tooltips for stuff that is actually standard? Because some of these are things that are in. Some of these are things
Yeah.
that are constructors in your code base. So obviously you have to know what they mean. But some of them are standard.
Yeah, I think maybe for like the HT profile, because already we have this like legend here, which explains like this stuff I was talking about with the heat profile. So we should probably have a little legend which explains what these things are. Yeah.
To elaborate on this question, how much does the non-profiling runtime actually know about what those thunks are?
The non-profiling runtime doesn't know what the thunks are to any detail, but it knows that they're different to each other, but it doesn't know anything about the source location or anything useful like that. And the runtime knows that the thunk has a certain number of pointers and a certain amount of data, but it doesn't know anything about the identity of where it's come from the source program, or a name of it, or where it lives, or its age, date of birth, none of that. Yeah. I think this question does raise a good point. I implemented, with the help of a lot of people, these tools. I also know how GHC works intimately. So there is a gap of knowledge of what I already knew and didn't think and thought everyone knew, but which is just not true. So
Okay, so to drill down further into this, so the names of this label column, those are just linker symbols. So it's not debug information. Right?
No, these are the types of the closure.
Right.
So they're not linker symbols. So on the right, so if we on the
Okay. So you look at the mod, what was it, home mod info
yeah.
constructor.
Mm-hmm.
I mean,
Right.
that name has to be in the...
Yeah, so the names of constructors are stored inside the names of constructors are stored so you can access them for this profile always, but then thunks have no additional debug information. So the name of the constructor is in some sense is debug information, yeah,
Okay.
which is very useful that it already existed in there.
And that's
But,
compiled into the executable
yeah.
without debug
Yeah.
flags. Okay.
Yeah. Okay. Right, so yes, I've just had slides for everything that I explained there. Right, so yes, what's very, 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 very useful is the ability to add user traces to your program so that when the event log runs, information, when the trace is hit, this trace will be put into the event log, and then event log to HTML will display this trace on the graph. So then you can correlate time with event in program much more easily, rather than trying to use the galactic brain and reason that yes, my program allocates a lot of thunks here. This must be the point that I think it is. Because usually when people start thinking like that, they're very deeply wrong. Right. So yeah. So I have the same one here. This is the same profile, but just with traces. And yes, go.
Actually illustrates a problem I have with events like HTML, which is that, okay, you started from showing us the grayscale screenshot of the old profiling and say, okay, you can't see anything. And now we have something that supposedly generates some interactive HTML, but it's not interactive, like it bakes in a lot of things at HTML generation time. Like, why can't I just say, okay, I want not the top 10, but the top 20, why can't I say, okay, I only see the events that match this label? Why can't I zoom in on a time interval? Like, all of these things, they seem to be baked in when you generate the HTML, instead of just being exposed in UI.
Yeah, I mean,
don't know what I'm going to need when I start.
It's a fair point. I think that when we started, we put more in the program generator part because we wanted to use existing tools to visualize the data and not write a lot of JavaScript to process the data.
You could generate HTML.
I'm just not an expert in generating HTML as well. So yeah, you could do, but it's just not how it's gone so far. Yeah. Okay, so you get your user traces into the program, and then when you hover over a particular trace, it tells you, okay, this is when GHD started parsing this particular module. And sometimes this gives you all the information you need, and you can then decide, well, this is the particular part of the program which is using a lot of memory, and you can dive into that. Question from Andreas.
I think event log to HTML already has arguments where you can set how many times it displays, set a filter on the name of the
But that's
times.
exactly what I mean. It's done at the wrong time. I'm going to do it while I'm running because I'm debugging one editing, right? I don't know how to have my whole process of what I want to do there.
Yeah, I mean, it sounds great. My contribution could have ended after making it colour, but I carried on a bit further. Yeah. So how did there's some utilities for putting these traces into the event log. So there's the trace marker utility, the trace marker IO utility. These just, instead of putting things into the console, put it into the event log, and then tools can pick them up. So this profile was generated with this command, which tells event log to HTML only keep traces that start with GHD started parser. Because if you don't do that, then the GHD puts a lot of traces in the event log, and you can't read the profile anymore, so it's not that useful. Right, Brian.
So when you add a trace, is it just like when that code gets executed, it like puts
Yeah.
a line in the trace.
Yeah. Yeah. Yeah.
Question with respect to profiling, sometimes whenever you run a forward profile, it's usually much slower.
Mhm.
Obviously, gives you a lot of information. What about those tracing and event log? Does it incur a lot of overhead?
And the event log doesn't incur a lot of overhead, no. The tracing, no. Not in the same way as profiling does. The question was, does adding traces add a significant overhead? But the answer is not to my knowledge, no. Yeah, go ahead.
When you add a trace like that, does it trigger a exploration of the heap so that you get a correct image of the heap?
No. You can implement that if you want, but no. It just when the heap, by default, when the trace is emitted, is not related at all to when the heap sample is taken. Yep.
Going back to the event log live thing,
Mm-hmm.
what rate of data are we talking about with the
I don't know. So the question was about event log live. What rate of data we're talking about with streaming? No. Shakes of head from the back as well.
Event logs can get quite large if you're running a program for hours.
Mm-hmm. Yeah, I don't know the answer. You have to investigate. Okay, how are we doing for time? What's
You're okay.
we're going good. Okay, so right, so we've got the high-level overview using HT profiling, and that hasn't resolved our problem. So it's time to get serious, I'm afraid, and that is when we start using info table profiling. And info table profiling is a means to get very fine-grained and accurate information about what is allocated on the heap. So what does that mean exactly? So to use info table profiling, you use the HI option rather than the HT option. And now, rather than counting by closure type, each closure which has a different info table gets its own bucket in the census. What implications does this have? Firstly, every different thunk in your program has a different info table. So now you can distinguish between all the thunks in your program very, very easily. Each constructor has its own info table, and each stack frame has a different info table. So you can really distinguish at a very fine level between all these different things that before were all amalgamated into single bands. The other great thing about info table profiling is that, as well as giving you very fine-grained profile and the ability to distinguish between these things, it gives you source locations about where they were actually in your user program. So, in particular for thunks, now when a thunk appears in the profile, you just get a source location about where it is in the program. And then, if it's a problem, you just go to that position in the program and fix it, and you can reliably know that you have going to eliminate that from the profile. The info table profiling works on its own without any additional options, but you just get a profile which is unintelligible, as all the labels will look like this column here, just an address, which most people can't interpret very, very easily. So in order to use info table profiling, you also need to enable the info table map. An info table map is a map from the info table address to information about that info table. So for this example here, we can see, well, this info table here corresponds to tuple coninfo. So this is more like the linker symbol you were saying before. And that type is a constr20, and the module that's defined in is ghg.internal.tuple. So this gives you a bit more information, structured information about closures, about constructors by default, but the real power comes from thunks. So we have a thunk here. It tells us the name of the thunk, the GHG gives it. It tells us what the type of the thunk is, and it tells us the source location. Now that is the key bit, and that is where the power comes from. So if I take this profile and search for thunk now, but in the constructor type column, I get a list of, I can see the lifetime of thunks throughout my program, and this kind of like observability really like allows you to investigate thunk leaks in a very precise and straightforward manner. Yeah.
Is there a reason you wouldn't always start with -hi and not ht?
Well, -hi requires the infotable map. So if your program's not compiled with the infotable map, then that is the reason. And also, like, let me open the profile. Sometimes these profiles are too the profiles are too fine-grained to be useful. Like this one's not too bad, but you can imagine a profile where the top 10 bands are just absolutely tiny. And at that point, it becomes quite hard to investigate the usage of the memory, because you might investigate the top bands, but if you eliminate some of the top bands, you only improve memory usage by 1% or 0.5%. So it's more useful to take a more holistic view of what's going on. Yeah, Michael?
What's the cost of enabling the infotable map? Is it a reason not to just always...
Yeah, so good question. So the infotable map, it does slow down compilation a bit, and it also makes your binaries quite a bit bigger.
But it doesn't change runtime much.
It doesn't change runtime at all, just because the binary has an extra bit in it, which is a map from infotable to. It doesn't change the heap layout at all. It's just an extra part. Yeah. Yeah, but you can't strip them out yet. But I'm tasked with improving that situation, so I will try and improve it shortly. Yeah.
If I enable the infotable for libraries.
Yeah.
And then compile the binary without it, does it still affect the binary size?
Yeah. No, so... Oh, I think it would, yeah.
Yeah? Okay.
Yeah. Yeah, I think it would. Yeah.
Do you recommend a specific compiler optimization level? Because I think I have the experience that inlining can sort of have an influence on which functions appear where in the diagram, and it can get very confusing because everything gets distilled into, for example, a functor instance. Then the source location doesn't make much sense.
Yeah, well, if you're profiling your program, you need to have optimization turned on, because otherwise you're not profiling the program really. That's my. I feel like if I want to profile a memory issue, I'm always doing it on the program people running production. That's my strategy. But your point is more like sometimes the source locations don't point you exactly to where you. That is true. Yeah, sometimes the source location is not extremely precise for some cases, like when you have like a functor instance and so on, and that is down to the heuristics that the source locations are chosen from. And in those situations, I'll use GHDebug typically to look more closely about what is actually happening. Yeah, go.
Isn't it usually the case that in core you have a stack of source locations that are accumulated during optimization?
Yeah.
So would it be possible to just close the whole stack for each?
You could do if you want to make your binary even bigger than it is.
But,
yeah.
I mean,
yeah. So it's a choice that's made at the moment just to expose one. There is a potential for exposing more. That was a choice that was made, and because I found it good enough to have one, and I could work out what was going on. So, if some people find they need more, then that is something that can be added. Yeah. So if I search, like searching for thunks is not. It's just nice. It's maybe the thunks are not necessarily the problem in your program, but it just shows like, okay, I can see quite precisely now where these are created in the program. So if you need even more, yeah, go. Yeah.
What is the size of that thunk? Like, is it everything that it holds onto? Is it everything that only it holds?
No. So no. It's only the exclusive size is only the size of the closures allocated on the heap. So if these thunks appear, there are thousands of thousands. So it's like infotable plus 2 words or something times 1,000. It's not everything beneath it as well. So this can't help you analyze, is my thunk holding on to a lot of information, that question is actually really hard to answer due to sharing, and just writing these analysis scripts uses too much memory typically. So it's just pointing out that you have 100,000 things in your program. Maybe you didn't need that many, or maybe you did. It just tells you, that gives you the ability to analyze, to look at your memory invariants and ask yourself the question, like, is this what I expect to see? Okay, so what time actually is it?
You've got about 10 minutes left.
Oh dear. Right, okay. Okay, right. All right, so distinct constructor tables is an extension to info table profiling. That is a shock. That's shocking. That's shocking. Okay, info table profiling is distinct constructor tables, extension to info table profiling that allows you to distinguish different allocation sites of constructors. So you can distinguish between different places where lists are allocated. For example, in fact, that is the example which I've shown here. So here I've searched in the description for : which are lists, and I can see, well, there are lists from GHUtils MISC 979, probably to do a map in my experience, or Concat or something like that. I can see there's some from OS string, file path, so on and so on. So it allows you to distinguish at a more of a fine-grained level. Right, so that's info table profiling. So now let's profiling by era. This profiling by era allows you to answer questions more about the lifetime of closures. For example, in this profile here, we have 3 phases of compilation. We have run 1, run 2, run 3. And in run 1, certain computation happens, and then we observed that all this information was retained during run 2, which does exactly the same thing, as you can see from the shape of the profile. And then after run 2, that's released, and it's all retained again through run 3. So we wanted, from this profile, this closure type profile, we couldn't really analyze what was going wrong or verify that fact, even though we thought it was true. Eras profiling allows you to tag each closure with an era, which is simply a word, and then the eras profile tells you how many closures from each era are alive at a particular point. So this is the same profile but using eras profiling, and now I can see, well, this dark blue is things allocated in the first era, and this lighter blue is things allocated in the second era. So I can see that all the things that are allocated in the first era are still alive in the second era as well. So this is like a more new profiling mode, which don't think it's really been used aggressively yet, but we found it very useful for our use case. So there's 2 ways to increase the era. There's automatic eras, which are increased when each sample happens, and then there's manual era control, which you can access using this set user era function, and that just writes into a global variable what the current era is, and when a closure is allocated, it marks that closure as being allocated from an era. Yes?
Does the era number have to increase monotonically?
No, you can set the era. The era is just a word 64. So you can kind of set, as any information you want to pack into a word 64, you can do it. So you can have high bits, low bits. You can increase it, decrease it. Set it randomly if you want. Probably less useful, but I'm not going to stop you. So then you can also use eras profiling with other profiling modes to inspect what is allocated in a particular era as well. So this is things allocated in era 1, but then separated by closure type. So you can see okay, things allocated here, when are they released? Do they go down? They can't go up, in theory, but the profile is a bit broken, and they sometimes do. Or do they stay flat, and you can inspect kind of things like that. Right, so some ideas for eras that you might find in your own programs. An era for each module that's compiled. That's a classic GHC one. An era for each phase during a module's compilation. Another one. I'm not very good at thinking of examples that aren't to do with GHC, by the way, if people realise that. The final one, I think of one. An era for each one of your albums. That seems to be that was more popular 1 or 2 years ago, but some say it's timeless. I don't know. So yeah, there are other profiling modes, but I don't find them that useful for various reasons, which I will skip over. Right. So I'm basically run out of time here, am I?
Yeah, I mean, lunch isn't for another 30 minutes. So
Yeah.
if you
Okay.
still have
Well,
things to say,
I have things to say, but I'll kind of reflect to the audience what they wish to learn about. So, okay. So that's about event log to HTML, and then I have quite a few slides about GHDdebug as well, which is way too much stuff. I'm sorry, everyone, but we can. If people are interested in that, then talk to me afterwards, or we can do a little bit here as well. Like I'm pretty easy about what I do. Question?
So the profiling runtime is useless, is what you're saying?
Profiling runtime is needed for eras profiling. The profiling runtime is also quite useful when used with GHDdebug, but I find it quite not that useful when actually creating heap profiles using event log to HTML. It's useful for the cost center profiling, definitely. Yeah.
So it's useful for profiling time.
Useful for profiling time, definitely. Heap profiling, not that useful, because you get basically all better information from input table profiling or from using GHDdebug, typically, in my opinion. Okay, how are people feeling? Like, what's the audience? Anyone willing to go out on a limb and say how the whole audience is feeling right now?
I think we'd like to hear about GHDdebug.
Yes.
Yeah.
At least knowing what it is.
Okay.
Do we have anywhere until lunch?
Right.
Somebody's hungry.
Yeah. Okay. So.
We're hungry for GHDdebug.
Yeah.
We're not allowed to go anyway.
You know. Yeah, we're locked in, and right. So we've got this kind of high-level overview now, which has got very high level to medium level, I'd say, and this is usually quite good for debugging your information, but sometimes you need precision. You need to just look at what is precisely going on and be able to answer precise queries, and that is what GHDdebug does for us. So GHDdebug allows us to answer more precise queries in the program, and the most important precise query is why exactly is a particular closure retained. That can tell you so much about your program and is something that is quite hard to work out from a normal heap profile. If I can get a stack of closures which say that this retains this, retains this, retains this, and I can look at it and just pick out the place that is incorrect based on my domain knowledge, then that is 99% of fixing memory usage issues. So my usual strategy is start with event log to HTML, see something that's wrong, and then into GHDdebug. Why is that retained? Oh, that's wrong. Fix it. Problem solved. So what is GHDdebug? How does it work? So GHDdebug is the first part of GHDdebug is you instrument your application with a simple wrapper using this with GHDdebug function, and then when your application starts, it creates a Unix domain socket in a default location, which can then be connected to, and information about the runtime can be queried by other programs. So you can write whatever program you want to query information about the heap using the APIs. But the main one that people use is this GHDdebug brick application, which is a terminal interface. So you start your application and you start GHDdebug brick, and then the view you get here is you start at the top. These are the roots of the garbage collector. So by default, it just shows you what all the roots of the garbage collector are, and from there you can traverse downwards to look at it if you wish. You can do whatever kind of inspection you want. It gives you that ability to interactively explore the heap. But what is actually more useful is that there are pre-canned analysis scripts built into GHDdebug, which allow you to answer these kind of questions like, what is retaining a home mod info? for example. So let me just get it up. Why not? So this is how GHC debug looks when you start it. These are the list of the sockets that are alive, and then you connect to one and start debugging your program. The other mode is the snapshot mode. So you can use the TUI to create a snapshot, which you can then save, and then you can read at a later point to do your analysis. Yep.
Could you please increase font size?
Anyone know how to increase the font size?
What terminal is it?
UXR GD. Control plus.
Control Shift.
I don't think you can in a live session.
Okay. Yeah. Sorry. That is a question I get. That is a question I get asked a lot. I haven't yet worked it out. So no. Is it unreadable? No. Sorry, Jessica. Well, I can't do anything about it. Okay, so I'm loading a snapshot here, which is.
Question. Live. Is this thing like as it's running?
So when you connect, you pause the process, and it's complete. It's just when you pause it, it just stops the process, and that's it. It stops it, and then you can inspect the heap, and then you can restart it, and then you can stop it, and so on. Yeah. So it's not mutating underneath you as you're trying to. That would be quite exciting, though, wouldn't it? If it was. Right. So I'm in my snapshot now, and which is again of a GHC compilation run. And like suppose that this is like the top level stuff, and I can just interactively go through it. But you don't normally start looking at the garbage collector routes because that's not that interesting normally. What you're normally doing is you press Control P and you get a list of all the different things that you can do. A bit like the VS Code command picker, but from 2015 rather than. Sorry, are we gone back in time? Sorry, I'm going crazy. Right. So these are commands that you can do. There's like the pre-canned commands, and the most useful one probably is the find retainers. The find retainers one. So if I want to know about why a constructor is retained, I search for the constructor name in the bottom, and then I press enter, and now what the program is doing is it is decoding, it's traversing the heap, decoding it as it's going, and looking for 100 paths from the garbage collector routes to these home mod info constructors. And once it has found 100 paths, it will stop doing the traversal, and it will display them to me on the screen. So now each one of these is a different allocation of the home mod info constructor, so I can look at each one. Home mod info is the type that GHC uses to for each module. This is where the information about the module is stored. So if I look at this one here, if I look in the right place, I could find out what module it was for. iFace mod info, module, fast string, distribution client command haddock. Right, so this home mod info is for distribution client command haddock. But what we really care about here is the retainer stack, which is this part 0 to 14, and it carries on going further down than that. And if you go all the way to the bottom of that, which is quite long, so it would have taken quite a long time to find if we started from scratch. It takes quite a long time to get there, not from scratch. If we go to the bottom, then here, line 439, we find the garbage collector route. So at the bottom of the stack, you have the garbage collector route, and then as you go up the stack, we can see that this thing retains this thing, 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 so on and so on. So if you can find something that is alive that shouldn't be, you can look at one of these stacks, and somewhere there's something retaining something that it shouldn't be. Like, is this thunk incorrect? I don't know. It might be. It might not be. Like, you can then have the ability. You then have the information you need in order to perform the analysis yourself, based on your understanding of the program. You yourself have come up with a memory invariant that this particular closure should not be retained. You have your reasons for that. So somewhere in this trace, there'll be a violation of an invariant that you have at least in your head, so you can find it and then you can fix it. So that is the most useful way of using GHG debug, in my opinion. Any questions about this? I might have skipped over because it's been very fast. Yes, question?
How do you know what the closure represents?
Which close? Like this line I'm on here? Any?
If I have a problem,
yeah. Okay. So.
I'm thinking in my source code, I have this particular expression. I suspect that may be retained. How do I find it?
How do you find it? Okay, so you can search by constructor name, which is what I searched for originally. So that allows you to search for normal Haskell constructor. You can also search by whatever other identifier you can't search by, like, Haskell identifier, but searching by constructor name is usually a really good one. And then, where are we now? So tip. Okay, where is that from? Well, there is information in this top pane up here, which tells me more information about what tip is, if you didn't know. So it tells you the type of tip is Word64 map. So then I can work out, well, tip is one of the constructors that comes from Word64 map for this particular example. If there's a thunk here, for example, right, so this thunk here, this thunk tells me it comes from unsafe duplicate into leave.io. And I can also press right on the thunk and look at what it retains itself, which can be quite instructive. But the thunk, it tells me that unsafe into leave.io, it tells me the source location. I can see, from my domain knowledge, I know where I've written that in my program, so I can start my analysis there. Is that kind of what you're saying? Like, I think this is all, it is like, this is a tool for experts. That's why I'm giving a talk here to experts. Like, you need some understanding about how the heap works. Like, it's not an automatic analysis tool. You need to have the question and the ability to interpret the results, but it's so powerful. Yeah.
So you've shown how you can do things like set the era within the program. Are there any hooks into the runtime that will let you say encode an invariant and then dump a snapshot?
Yeah. The question is, are there any means to encode into runtime memory invariants and then dump snapshot when it happens? The answer is no at the moment, but we have thought about that would be a good idea. It's just never like come up. Yeah, Travis.
I once had the great fortune of attaching GDB to a process that also had GHC debug attached. It's actually quite useful for like copying pointers from GHC debug and then doing something within the GDB.
Yeah, you can do that. Yeah.
It's quite a pain because there's a different notion of like GDB debug has a certain notion of what it means for the program to be paused. Different from GDB's opinion about
Yeah.
and I've kind of had this vague fever dream sense that like it really would be nice if GDB and GHC debug somehow knew about each other. Am I the only one thinking about that?
Yeah, I suppose my opinion is like typically GDB is not actually useful for debugging Haskell programs. My experience, I mean, I know like Simon was saying like if you really need to like debug the runtime, then it can be useful. Like, are you frowning, Simon? There. Yeah, like that's my general perspective. Like, use a program, like if you're debugging issues in the runtime, then GDB is too low level for debugging user programs. Oh, I see. Yeah. So I personally haven't had like that much need for kind of debugging issues like that. But it does sound like if they did align more nicely, it would be better.
Doesn't Zubin have a prototype of that?
Zubin has a prototype of we can load a core dump into GHC debug, which is a similar idea of integrating GDB with like with GHC debug, but it's not I suppose you could also load the core dump into GDB. But if you don't,
Does that work? That would be quite compelling.
Yeah, it does work. It's not merged. There is code that does it. It's not merged because not clear how robust it is and how maintainable it is. But yeah, I mean, people have done it, at least 2, and it wasn't me. Right, Duncan.
So there was a discussion a moment ago about, wouldn't it be nice if we could run a script that would check, some violations at the very end, on every profile or whatever, each sentence. But isn't it not that far off? Because you can run custom scripts within GHC debug.
Yeah, you can.
But couldn't you also arrange to have GHC debug, run and then unpause the program up until the next major GC, pause, run the check again, unpause, carry on, and just do it like that?
Yeah, but running analysis scripts is pretty slow in GHC debug side. I think it would be more profitable to write simpler scripts in C, or have simpler invariants you could have in C.
You think it would be dramatically quicker to be able to?
I mean, it took 23.3 seconds to find 100 paths to these closures, and.
But is that not simply because that's the amount of work you have to do that? Or wouldn't that be much quicker?
No,
it's
much faster to do it in C, yeah. Okay. Maybe I'm just not implemented it very well, but there's quite a lot of overhead in GHC debug of decoding the closures into Haskell data types.
So I have a question about the UI. It seems like the tree is sort of following the topology of the heap, but like when you were exploring the retainers, it collected them all into a list, which is reverse sorted. How do you navigate the list of retainers?
You press up and down.
Sure, but how do you know what refers to what, other than the backwards?
Well, 1 refers to 0, and 2 refers to 1, and 3 refers to 2.
So the retainer list, so that the chain is 500 long?
Yeah.
Oh, okay.
Yeah, so a chain is 500 long, and when you get to each one, you can press right, and then you can inspect information about each one if you want. So here I can see that this tagged value refers to a home info, which was yeah. So do we have time?
Yeah, is it quick?
It's Gergo, probably isn't quick.
So in this particular example, as you were scrolling around, we saw that it's basically the prep stage of GHC being lazy.
Well, I didn't.
Is this like a bug in GHC?
No, I didn't particularly anticipate there was a bug, but maybe there is. I didn't expect it to be this long. I didn't look at it before doing this example. I mean, this does look wrong, doesn't it? But
like Prema not doing anything, just preparing to do something.
Yeah, maybe it is wrong. But I don't have a memory invariant in mind, so I couldn't possibly tell you.
So I'm going to quickly abuse my position here for a little bit and kind of ask a meta question, right? So one thing I've noticed in my years of seeing talks about debugging and debugging tools in Haskell is invariably every time there's a presentation on some of this, a huge proportion of the audience goes, I didn't know this existed. Right? Like every time, like without fail. And I know there's blog posts about it, but like where are people, is it that you're Googling, is it an SEO problem? You Google like debug Haskell program and the newer tools are just not showing up? Like where's the disconnect? And this is, a question for Matthew, but also more generally, right? Like there seems to be a kind of communication break. Am I alone in thinking this, or you're not?
Well, why does none of the tools have profiling in the name?
Yeah. Well, okay. Well, but right, there seems to be like the people making the tools are making very cool tools, and then the folks who can best benefit from them are sometimes not knowing these tools are available. And that seems like a problem worth solving, right? Like
sometimes you learn one way to do it, and then you don't look around for new.
That's a fair point. Yeah. Okay. Okay. So people just stuck in their ways. Yeah.
I
Yeah.
think it's also like unless you're like following like developer blog, like and you see the post, these things as they're like the blog post has come out, like
Right.
it's very rare that like a year later someone's like, oh hey, there was this thing that happened a year ago.
Right.
So
Right.
it's very easy to miss it unless you're like drinking from the stream.
Fair point. Yeah. Yeah. Yeah.
Do you have a website where we can list all the tools by category?
Yeah. So kind of like a federation of
Yeah.
that. Yeah. Fair point. Yeah. You were going to try.
Knowing that the newer tools work with the GHC that you're stuck on for your.
That's probably that's a fair concern, which is it's not necessarily true. Does this have constraints on which GHC it works?
I think it's working on GHC to 9.4 maybe.
Okay, but there are folks on 8.10 or that, so.
Yeah. There are lots of different ways of doing it. Like Matt listed like 8 different profiling options. Apparently, like 7 of which are bad and shouldn't be used. So if you look at the GHC user manual, you're like.
Right. Right. Yeah. So this goes back to like.
User manual won't even if you read the GHC user manual, it'll tell you like a decent amount about cost center profiling.
Right.
You can like read the GHC user manual and kind of get started with cost center profiling and work out that maybe you need and you find a nice tool to view it. But I'm not sure you can kind of realize from the GHC user manual that there is a world of heap profiling available to you.
Right.
Yeah, I suppose I'm in a difficult spot there sometimes because I want to edit it, but then I don't feel like able to just advertise everything that I've done in like which are external to GHC repository in the GHC user manual. Like.
That's the problem. Can we place?
Yeah.
We can put it in the GHC user manual.
Like.
Yeah. So this
GHC user manual is great.
You want it to be in the GHC.
Yeah, because the users read the user's manual.
Yeah.
For the users, by the
But
users.
this is a good point. This is something we should probably think about. But
like
it might be that it belongs in the manual. That's fair. But if you're saying you're shy to do that, then we should make it clear that you don't need
cost
to.
center profiling, the GHC user manual tells you about the stuff that's built in the GHC, which is you get a kind of unusable report.
Right.
But then that at least gets you to the point of like, oh, there's information here, maybe I could look for a tool to interpret it better. Whereas it's not clear that is it event long to HTML in the GHC?
It is. I did put that in. Yeah.
Okay, then maybe I take it.
I guess this can be solved by one layer of indirection. Have the manual link to a wiki page, and on the wiki page, all the tools useful for that can be listed.
Yeah.
Okay. Yeah. Last 2 points, and then we go.
Yeah, also, what would be nice is a recommendation what tool to use if you don't know anything about this.
Yeah.
If you've got 10 tools.
Yeah, so this is a thing that comes up a lot, which is like codification of best practices is lacking generally.
I think one issue with these tools is even if you know about them and you even have a blog post explaining them, there's always just a very simple example that's easy to diagnose. And then you have your own program and try to solve your own issue, and it's so different from the example that you saw that you have no clue how to diagnose your program using the tool. So
that's.
I think it's also an issue of documentation because you have to have a very large background knowledge to even understand what's going on there.
Yeah. Okay, this is really the last thing.
I also have like a bunch of tools. So like if you use a Java profiler, you connect the Java profiler. It does time profiling. It will do heap profiling. It will have like different visualizations. Whereas if you want to debug a Haskell program, it's like you can use event log to HTML. You can put your GHC cost center profiles through like 5 different tools that plunge them into different formats and present them in different ways. Like there's already 2 different ways of visualizing the stuff from heap profiling. It would be helpful if GHC, if there was something that just had all of that accessible. So you'd be like, how do you debug the runtime characteristics of your Haskell program? Connect this thing, click around in the UI, you'll find the stuff.
Integrated in HTML?
Yeah.
Well,
yeah. All right. Well, let's thank Matthew for.